14.5, expected value. So in the game shown over here with the spinner, you can pay $1 to spin the arrow. If the arrow stops in the red space, or sort of peach, you get $3. So you get the $1 that you already paid and 2 more. Otherwise, you're just going to lose that $1. If you play this game many times, how much would you expect to win or lose? Well, so you're going to want to consider the probability of getting red or the probability of getting blue. Now, we see that there are 3 spaces with red, right? We have 1, 2, 3 spaces with red. But with blue, we have, 1, 2, 3, 4, 5, 6, 7 spaces with 7 spaces with blue. So what's this mean? Remember, with red, that's 3 out of, that's 10 in total. With blue, we have a 7 out of 10 chance of spinning. So what we want to do is consider our options here. Now, if I spin, did we say how many times? Let's say I spin, 1,000 times, right? If I were to spin 1,000 times, so let's just add some extra zeros here, 1,000 times, that would mean I should land, theoretically, on red 300 times. Well, if I spin 1,000 times, that also should mean I should land on blue, theoretically, 700 times. So let's think about the money here. I should make $2, right? I'm actually making $2, right? Because I spent $1 and I got it back. I should make $2 every time I hit red. Well, that's 2 times 300 times, right? Plus, I'm going to lose $1 every time I hit blue. That would be out of 700 times, all right? So in 1,000 games, that means I should lose $100. That's what I would expect to have happen. So E, or our expected value, is going to be basically based on this. We're just going to divide that by 1,000. Our expected value is how much we're expecting to make out of the number of times. So when we divide, that's going to give us, about negative 0.1. Okay, so that means each time we should theoretically lose 10 cents. There's a more mathematical way to do this, though. We could think of this as being the payoff times the probability plus the payoff times the probability, or however many of these there are. So because we ended up dividing this by 1,000 anyway, we could really think of this having been the payoff times the probability, which was, really 3 out of 10, when that's simplified, plus the payoff times the probability, 7 out of 10. And that's going to give us that same answer. So our expected value is basically our expectation, and we actually talked about this a little bit in statistics. The expected value in an average expectation per game, or is the average expectation per game, if the game is played many, many times. So in general, E does not need to be one of the possible payoffs, right? Negative 10 cents was not part of the expectation, right? Adding 2, subtracting 1. It's just kind of in general what would happen. So notice that it's obviously impossible to only lose 10 cents in this game. That's not how it works. But they're saying over time what would happen if we play this a bunch of times. Kind of what should we expect on average each time to occur. So here, let's say we are rolling a die. We're going to assume a fair die, and you receive $1 for each dot that shows. What is your expectation? All right, so we're going to use this formula. So if I roll a 1, I should get $1, and rolling a 1 is 1 out of 6. If I roll a 2, I should get $2, and rolling a 2 is 1 out of 6 probability. If I roll a 3, I should get $3, 1 out of 6 probability. 4, 1 out of 6. 5, 1 out of 6, and 6, 1 out of 6. Whoops, getting ahead of myself here. 6, 1 out of 6. All right, when I work that out, that should give us 21 over 6, which is equal to 3.5. So what I should expect is that I should be getting $3.50 per game. Obviously not perfect because that's impossible to get, but it's kind of an average expectation. Okay, In Monte Carlo, the game of roulette is played on a wheel with slots numbered 0 through 36. The wheel is spun and a ball is dropped in the wheel, and it is equally likely to end up in any one of the slots. There's no trick to this. So in order to play the game, you're going to bet $1 on any number other than 0. If the ball stops in your slot, you get $36. The dollar you bet plus an extra 35. So we want to find the expected value of this game. All right, well, you are going to gain $35 with the probability of 1 out of 37. Remember, this is actually 37 numbers here, right? 0 included. So you should get $35 as long as it lands on the one that you picked. So that's 1 out of 37. Plus, you're going to lose $1 every other time. So that's 36 out of 37. So if we calculate this, that's going to give us negative 0.027. So what that really means is you should lose, let's round that a little better, negative 0.03. That means you should lose 3 cents every dollar you bet.